Here we go. I don't know if you remember how we talked about the electric motor. For the electric motor, we supplied a current from this end to get the armature to spin, and that gave us motion. Now we're going to ask ourselves, what if we supply a rotation from this end, maybe through a turbine by having water go through it, like in a hydroelectric dam, or maybe from a nuclear plant by having the nuclear power create steam and then sending that steam through a turbine. Generally, there's some kind of a turbine, some kind of a turning device. How can motion create electricity? If electricity can create motion, how can motion create an electricity? So this is the generator. It was invented, Mara, by Michael Faraday, although for what it's worth, he called it a dynamo, if you look at the old literature. And I think they still call it that in Britain. Generator, a dynamo. The previous figure shows a simple hand-operated generator with only one coil. So imagine off the page, there's a handle right over here somewhere that somebody is cranking. Really, we're talking about one of these, a hand crank flashlight or something that you crank to recharge. Okay? So we are supplying the motion. I want you to notice what happens. So if it's spinning this way, let's put a little proton right there. I think the proton, right when it gets to here, is going to be moving down the page. So can everybody point your right thumb down the page, please? What direction is the magnetic field? Magnetic field lines always point from north to south. So you're going to point your fingers to the right. You know what? The charge is going to feel a force this way. Oh, and on the left side of the armature, the charge is going to feel a force this way. We're going to get current if we connect it to these brushes and these slip rings. So read along with me here. It says this: when the coil is rotated, the two long sides of the coil cut across the lines of force of the magnet, and a varying EMF is induced in these two segments. This is going to explain why we have alternating current coming out of our outlets. Even though a lot of our devices run on direct current, it's much easier to create alternating current. So here's a side view. When the coil is vertical, the proton sitting right here is moving to the right. You know what? It's moving parallel to the magnetic field. If it's moving parallel to the magnetic field, is there any force on the proton at all? No. And so right at that moment, you get zero voltage. If you hooked up a voltmeter, the needle wouldn't move. But now when it's moving in this direction right here, the proton is moving down the page. If you point your thumbs down the page, magnetic fields to the right, your palm should be pointing out of the page. When it's in this location, in the right-hand part of the armature, we'll have a current flowing towards us. In the left-hand side of the armature, we'll have a current flowing away from us. We would get an induced voltage, and in fact, it'll be at its maximum right when it's in that position. Then we're going to get another zero because A and C are the same picture, Sadie, except now the top has become the bottom, the bottom has become the top, but they're still moving parallel. And then D, we get the maximum, but because the armatures have switched sides, the sides have switched ends, you're going to get, we'll call it a negative voltage. And what you get is a voltage that looks like this. It hits a maximum, goes to zero, hits a negative, don't write this down, hits a maximum, goes to zero. Who's done pre-calc? What's that a graph of? It's a trig function. It's a sine. Any sine graph is also a cosine graph, is also a sine graph. You can turn it into a sinusoidal. It's a sinusoidal trig function. Yeah. And that's why we don't look at AC in detail in physics 12, because I can't assume you've taken pre-calc 12, but it is kind of neat. Oh, absolutely. It's a trig function. You get an induced EMF. So when the coil is horizontal, they're perpendicular, you get a peak voltage. Then it begins with the coil of the generator perpendicular to the lines of force. If you just look at the top segment, well, you know what? The voltage is going to be BLV, like we talked about yesterday. You can look at the length of wire. It's going to be B, the strength of the magnetic field, L, how long the wire is, V, how fast it's turning. So what that means is the faster I crank this, the more voltage I'll generate. Yes? The bigger the generator, the more voltage you generate. Stronger the external magnetic field, the more voltage you'll generate. Okay, when it's at the top position, it's perpendicular, and so it's 0. This is, again, really saying if you want to, on the next page, is it turn the page? Yeah, you can draw that, and you can just do a quick sketch. The voltage, yeah, it's sinusoidal, Jonah. It's sinusoidal. It's going to look like that. And it can be a sine function or a cosine function, depends what your phase shift is. Okay. So here's the question Faraday asked. How can we combine induced voltage in a wire and induced voltage in a loop of wire? Is there a way that we can combine them into one Uber law that fits them both? Yesterday and the previous day, Ella, I showed you how we can induce a voltage by just dragging a wire sideways through a magnetic field. Here we're spinning a coil in a magnetic field. We definitely get an induced voltage in both. How can we combine them? So here was the first thought that Faraday had. Consider the following example. We have a rectangular loop of wire moving to the right, and it's moving perpendicularly to the magnetic field. I was very proud. I took about an hour to make up this diagram. What do those dots mean? The magnetic field is what? Okay, out of the page. And what I'd like you to notice is I'd like you to look at a charge right there. Okay? You can draw him right there too. What direction is that proton traveling? What direction is the coil traveling? To the right. So can all of you point your thumbs to the right, please? What direction is the magnetic field? Out of the page. Which way will that proton get pushed, Scott? Up the page or down the page? Okay, right here at location B, we're going to get a current flowing in this direction. What about in location C? Well, again, we have a proton here. It's going to get forced down, but this proton, the back half of the coil, is now also in the magnetic field. What direction will that proton feel the force, Scott? Same answer. And so what you get are two opposing identical currents. When you have two opposing identical voltages, what is your net current exactly as a number? Nothing. And in situation D, nothing. Ooh, but in situation E, when part of the coil is out, now this is no longer going to be affected, but this proton will be affected, and now you're going to get a current flowing in that way. In situation A and situation F, no current because they're not in the magnetic field. So where will it be an induced current? Right there and right there. Is that okay? This is where Faraday had his aha! Well, this is where he had his realization. To explain this, he realized that a voltage, and therefore a current, in a coil was induced when the area of the coil that was exposed to the magnetic field changed. He said, you know what? The reason we're getting a voltage here is because none of the area is exposed. Here, all of the area is exposed. Right here, the amount of area that's being exposed is changing. That's when you're going to get an induced voltage and therefore an induced current. And this is going to bring us to the notion of magnetic flux. Okay? What is magnetic flux? It's the number of lines of magnetic field passing through an area. It's how much magnetic field is passing through an area. But I'm going to say how many lines of it because we're going to have to think about how this all fits together. Okay. Symbol, this Greek letter here. You draw a circle, you draw a line through it, and you do that. It looks like a TIE fighter on its side. Except we're lazy. Nobody, when they're that's what it'll show up if you find that Greek letter and you go to your Greek keyboard and you type it. But most of us just do a circle with a line through it. We don't put the wings on the TIE fighter. Units. Magnetic flux is measured in Webers. Abbrev. Why can't I just use a capital W? That's watts. This is one of the few two-letter units. There's a few out there. Hertz is another one. Okay. Sorry? Sievert, yeah, there's a few. Okay. How do we calculate flux? Flux is defined as the strength of the magnetic field times the area. Except the magnetic field and the area need to be perpendicular. Let me show you what I mean. I think the easiest way to show you is to clear this diagram, to give you just a pure white diagram. Ignore the top part. You can think about the magnetic flux as how many beams of light are passing through this loop. Okay? Right now, the loop is parallel to the beams of light. How many beams of light are passing through this loop? Be obvious. This would be zero flux, maximum flux. How can I make the flux stronger? Well, one way would be, if we're talking magnetic flux, move your coil closer to the magnet, because now way more beams of light are passing through the loop. You can see the area of the shadow got bigger. How can I make it weaker? Do that, and I can do that in two ways. I could either make the bulb weaker, make the magnetic field weaker, or I can move the coil further away from the magnetic field. And so magnetic flux for a coil goes from 0 to maximum to 0 to negative maximum, because now the top is on the bottom and the bottom is on the top, to 0 to maximum to 0 to negative maximum to 0. It says, example 1, for each orientation of the spinning loop pictured below, what can be said about the amount of flux passing through the loop? Which one of these will have the most flux, A, B, or C? Okay, so I'm just going to write here very high tech. I'm going to say flux equals max. Which one will have no flux? Flux equals 0. In B, is the flux increasing or decreasing? Because it's rotating to picture C. This would be decreasing flux. Is that all right? Let's look at a bunch of pictures here and see if we can figure out whether the flux is increasing or decreasing. I'm going to zoom in. You need to imagine that the coil goes like, I didn't draw it in because it cluttered up the diagram. So this is like a side view. Oop, Mr. Dueck, let's go back here. If the magnetic field is getting stronger, will that increase the flux or decrease the flux? Scott? Yeah, so let's say flux, I'm doing my flux messy. Boy, I have a tough time getting that line in the middle. Increases. Cole, what about picture B? If the magnetic field is decreasing, what's happening to the magnetic flux? Also, yep. Those are the easy ones. Now let's, What about here, where the area of the coil that's inside the magnetic field is getting smaller? What's happening to the magnetic flux then? Yeah, flux is decreasing here. D. What about here? This was Faraday's aha moment. The area is increasing. What area? The area behind the bar. The area behind the bar is getting bigger. Flux is increasing. This was how he was able to link the bar to the concept of flux. E is a trick question. Shko, is the flux increasing or decreasing in E? It's a trick question. It's a trick question. Yes. Is the area that's being exposed to the magnetic field changing at all? Say no. Is the strength of the magnetic field changing at all? Say no. So if flux equals B times A, if B isn't changing and A isn't changing, this is a constant flux, and because of that, no current. Ooh, okay. Mesa, what about F? Think about the size of the shadow. Now, here we're moving the magnet closer to the coil, but I think that's mathematically the same as moving the coil closer to the magnet. What happened to the size of the shadow? Increase or decrease? What happens to the flux? Increase or decrease? This is going to increase the flux. What if we're spinning the coil? Well, first of all, Dan K, right now, is the flux at its maximum or is the flux zero in the picture right now? And I think we're going from maximum to less. You know what? This is a decreasing flux. What about H? If we're making the loop smaller, what's that going to do to the flux? Decrease, because flux is magnetic field times area. If area is getting smaller, this is going to decrease the flux. Is a really, really tricky one. So here's our coil of wires. Well, if the current is getting bigger, the magnetic field around the wire is getting stronger, which means this is the same as the diagram right above it. Mathematically, the magnetic field is getting stronger, whether you're moving closer to the magnetic field or in this case, bumping up the current. Here, the flux is going to be increasing. So previously, we said an induced voltage was created when we changed the field, the orientation, or the area. We can now just summarize all that. Ethan, there's an induced voltage when flux changes. And you can change flux by changing the magnetic field, by changing the area, by changing the orientation of the area, which is really like changing the area, or both. Faraday found that the amount of voltage varies directly with the flux change. More flux change, more volts, which means this is going to be on top of the equation. When it gets bigger, voltage, EMF gets bigger. Inversely with time, there's going to be a T that's going to be in the bottom of the equation. The faster you spin it, the smaller the time, the more the voltage. Oh, and directly with the number of loops of wire. We've been looking at a single coil of wire. You want to double your voltage? Put two coils in there. You want a 1,000 your voltage? Make it 1,000 turns of wire. And so that gives us really accurate control in a generator over how many volts we want the generator to output. We can customize it to however accurate you want to be. So there's going to be an N on the top. And this is going to bring us to Faraday's law. It says the induced voltage created in a coil, or coils plural, of wire is given by negative, capital N, delta flux over delta T. Let's start with the obvious ones. What's delta T? Yeah, and time is always a change in, and much like we've done, we'll often just get sloppy and not put the delta in front of it, but this is change in time. Flux is, oh, well, really, I should put a delta in front of this. What's delta? This is going to be change in flux. By the way, what's change in anything? Often you'll go final minus initial. And N is the number of coils of wire. Often they'll just say a coil, which means N is 1, but if they give you the number of turns, it goes there. What else is standing out in that equation that you're wondering about? Why negative? I'll explain it tomorrow. Very cool. One of my favorite laws called Lenz's law. Example 3. A circular loop of wire of radius 2.5 cent. Nice try, Dueck. 0.025 meters is in a magnetic field of 0.4 teslas. It's removed from the field in a time of 0.05 seconds. What's the average induced EMF? And it says the axis of the loop is parallel with the field. Okay. Which means the area of the loop is perpendicular. Alrighty. Right now, there will be no EMF. Right when the bottom starts to exit the magnetic field, that's when we'll start to induce a voltage, because that's when the amount of flux is changing. And then as soon as it gets to this position, when it's completely out of the magnetic field, back to zero again. Okay. Jonah, what does it want us to find? The average induced EMF for a coil. This is going to be Faraday's law. So our new equation, E equals negative N delta flux over delta T. Oh, how many loops of wire? What's N? It says a loop, a circular loop. So N is going to be 1 for the rest. You know what? Since this is new, let's do our little DFIC approach. N is going to be 1. Oh, and Jonah, what's delta T? They told you. Don't overcomplicate it. Go read. Delta T. Change in time. Yes. Capital T is Teslas. That's magnetic field. Okay. What we need to find is the change in flux. I'm going to change colors. Well, what's change in anything? How do I calculate flux? By the way, I think how to calculate flux is on your formula sheet. Yes? I think it does say flux equals B times A. And then it does have Faraday's law, E equals negative N, change in flux over change. Okay, so I gave you both of these. Actually, I can figure this out. First of all, what's the final flux? Look at this picture. What's the initial flux? Look at this picture. Well, we're completely in the magnetic field, so it's going to be the magnetic field times the area. You okay with that, Raj? Jonah, what shape is that coil? Starts with letter C. What's the area of a circle? Did I give that to you on your formula sheet where I have the trig stuff? I can't remember. Did I give you the area of a circle? Okay, pi r squared. Okay, so you ready? It's going to be 0 minus, the area part is going to be pi r squared. Oh, what's the magnetic field, Jonah? They told you. There's the 0.4. By the way, 0 minus anything is just negative that thing. Is that okay? So I'm just going to stop writing the 0 because that's not going to make a difference. Let's crunch this on our calculator. It's going to be negative 0.4 times pi times 0.025 squared. What is the change in flux? Yep. It's got to be negative, isn't it? Okay, well, geez. Negative 7 point. I'm going to carry the extra sig figs because this is not my final answer. Times 10 to the negative 4. Units. It's our new units of the day. What do we measure flux in? Webers. And Jonah, that's going to go up there. So now we're good to go. We can crunch this. The EMF that we're going to get is negative. I'll put the 1 in my notes. In your homework, if it's a 1, Sadie, do I make you write? I don't care, but I'll put it in so you know we did count the number of coils. I'm just going to use my answer button. So I'm going to write A and S because that's what's going to happen here. Divided by 0.05. Oh, what's nice is the negative in Faraday's law cancels out with the negative in my flux, and I do actually get a positive voltage bonus. Jonah, what'd you get when you're done? I don't think it's going to be, I'm using my notes from a couple of years ago, so I'm not doing these in my head, but you don't get a very big voltage, right? Is it 0.016? And the units for EMF or voltage is volts. So not very big, but at least it proves the point. A much better method, rather than pulling it, spinning it. That's why almost anytime you're recharging something manually, you're turning a crank, or for a generator, you're spinning a coil, or for a hydroelectric dam, you're turning the turbine. It's spinning it works much better. So I don't like the previous example, but ooh, I like example four. I like example four. I like example four. Example four is a nice question. Dan S., what do they want me to find? The average induced EMF. Okay. Is it a bar or is it a coil? If it's a bar, I would use BLV from the other day. That's a coil, so I'm going to use Faraday's law. Here we go. Faraday's law says the induced EMF is negative number of coils delta flux over delta T. Because there's a lot of information and because often you're finding the change in flux separately, I'm going to do my DFIC approach. I'm going to list my data. Daniel, what's N? How many coils of wire? How many coils of wire? How many coils of wire? Keep reading. Yeah, dude. By the way, I did notice you caught that, and so I should have done that. Oh, what shape is the coil? Oh, what's the area of a square? It's just one side squared. That's why we say squared for the power of two. Okay, so I'll get that in a second. I'll come to that. What's the delta T in this question, Daniel? You know what? 0.002 is less. That's 2 times 10 to negative 3, but that's less typing and writing. Okay, let's find the change in flux. I often do that separately. If you get really good, you can do all of this in the main equation in one step, but I typically go, okay, change in flux. Oh, Dan, what's change in anything? Okay. It's starting out perpendicular and then it's rotated 90 degrees. If it starts out like this, perpendicular to the beams of the magnetic field, and it rotates 90 degrees, what's the final flux exactly as a number? Bonus. And then the initial flux is going to be B times A. 0 minus anything is just negative that thing. Daniel, what's the magnetic field strength? What's the area? It's a square, so I guess it's going to be 0.05 squared. What do you get for the change in flux? I'm going to write that in scientific notation. I think the 5 is the fifth digit after the, yeah, negative 5 times 10 to the negative 5 units for flux or change in flux. Yep. And that's going to go over there. So here we go. Negative 100, negative 5 times 10 to the negative 5, or you could just write answer button, divided by 0.002. Crunch that, my friend, and tell me how many volts this would be. I don't think you get a negative answer. I'm pretty sure I see a negative times a negative, which is a positive. Do I not? Right? Right? Yeah. And by the way, the negative, if you said that, I would give you credit because really it depends on what direction you let the magnetic field be positive and what direction you let the magnetic field be negative, because magnetic field is a vector and you might decide to let one way be positive, Alisher, and you might decide to let the other way be positive. I'd have to give you full credit. So what was it? 2.5 volts? Okay, this is a little better. Now we're closer to a battery. Getting there. We can also change the flux by changing the magnetic field. Magnetic field is a vector, so we're going to have to, Ethan, call one direction positive and one direction negative. Ethan, it says this a circular, okay, it's a circle. I'm going to do pi r squared. With how many 100 turns of wire? It's exposed to a changing magnetic field as shown below. If the field takes 0.12 seconds to change, what's the average induced voltage? Ethan, what direction is the magnetic field in the first picture? In the first picture. Isn't it into the page? It just says, okay? What direction is the field? What does it say in the second picture? Yeah, I couldn't get the dots and things to work properly. So the first one's into the page, second one's out of the page. Are those two different directions? Say yes. We have to let one way be positive and one way be. Which one do you want to let be positive? Which one do you want to let be negative? You know what? You know, a good trick. If I want the negative and the negative to cancel in my final answer, I would like the change in flux to be negative, which usually means I think I want final to be negative and initial to be positive. That'll guarantee I got a negative answer. So I'm going to let this be negative and this be positive. What are they asking me to find, Ethan? It's going to be Faraday's law, negative n change in flux over change in time. What's n, Ethan? How many coils? 100. What's delta t? 0.12. You know what? We're going to have to find change in flux. I'm going to do that over here. What's change in anything? Yeah, and this time neither of these is a zero, so we're going to have to do some crunching. It's going to be magnetic field final times area minus magnetic field initial times area. Ethan, what's the final magnetic field? Careful. Good. Negative 5.4. What's the area of a circle? Pi and r is 0.1 squared. Yes. Minus, what's the initial magnetic field? Now, by the way, Sadie, if you decided to let the 7.8 be negative and the 5.4 be positive, you'll get the same magnitude difference. I'd give you full credit. I have to, because we're really deciding arbitrarily which way is positive and which way is negative. 7.8 times pi times 0.1 squared. You should be able to type that in one line on your calculator. You're going to get a negative answer. I have the numbers in front of me. I didn't do this in my head. Try this, but you should get negative 0.4 something, 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 something. Get it, Ethan. Let me know what you got for the change in flux. Point. Okay, negative. Start over. Point. Yeah, 4147 and change, right? And we're going to use our answer button anyways. So, okay, here we go. EMF is going to be, what was N? Ethan, I scrolled down. Was it 100? Answer button, or negative 0.4147 divided by, what was delta T? What will this setup generate? Induce. You get, sorry, how many? Ooh, okay, that's something. Now that's a fair bit of voltage. We can work with that. Now this is becoming a generator. Okay. Now, the easiest way to flip the magnetic field is not to flip the magnetic field, it's to flip the coil, because by flipping the coil, now the magnetic field is coming through in the other direction. And so that, again, is why every generator spins a coil. Example 6 says, rank the following in order of increasing induced voltage. Okay. Which of these would create the largest? Oh, sorry. In order of increasing, which of these would create the smallest? Start with the smallest. I'll give you a hint. One of these will have zero induced voltage. Which one? No. A is completely the wrong answer. C is completely wrong. Remember, what causes voltage? A change in flux. Which one does not have a changing magnetic field or area in it? Which one? No. No. B. Look. Same area, same number of magnetic field lines, same area, same number of magnetic field lines. Was there a change in flux at all? No current. So B has zero. Which one has the next smallest change in flux? D. That would give you the next biggest voltage. Yes. A, some of you said that's no, A would give you the biggest change in flux. You'd get the biggest voltage, the biggest induced voltage from it because you're going from full flux to no flux. That's a massive change in flux. Okay. So, technical comment for induced voltage, symbol for both of them is EMF. If it's a wire, use BLV. Oh, that L didn't go through. If it's a coil, use negative N, change in flux over change in time. That's how generators work. In an electric, by the way, that means every electric motor is a generator, is an electric motor, is a generator. In an electric motor, we supply the current to get motion. In a generator, we supply the motion to get current. You can take apart any old electric motor, like if you have an old kitchen fan that's broken. If you take that apart, there's an electric motor in there. If you spin that electric motor by hand and clip wires to the input, you'll get current coming out instead. You okay, Declan? You gonna make it? What's your homework? Try number 1. Try number 2. 3 is good. 4 is good. Skip 5. By the way, helicopter blades are sweeping coils. You can think of the blade as a long piece of a coil through the Earth's magnetic field. It does induce a voltage, and it's something they have to really take into account. If you're, for example, rescuing someone from a cliffside using a long line, you have to take into account that your helicopter is probably at a different voltage than that person, and it's possible for that person to get very, very badly shocked if you're not careful. But we're going to skip it. 6 I'm going to pass on. 7 I'm going to try. 7, they didn't tell you the time, but they told you it's spinning 120 cycles per second. So maybe you can figure out the time for a quarter of a turn. If it's spinning 120 times every second, how long would it take to do a quarter of a turn? If you can't figure that out, that's okay. The rest of it is fairly plug and chug. Also, from the review, you can now do a whole bunch of questions. You can do 5. Oh, Can all of you cross out 7, please, on the review? 7, for some reason, number 5, the picture reprinted itself partly at question 7. So just cross out number 7 on the review. You can do 12. 15. 16. 23. 24. 32. 34. 36. 37. 39. If you want to get a head start. Let me hit stop.